So while we were on the break, some of the students said, well, can we also continue the homework and look at problem number 139? And the answer is always yes. We can do that. All right, and the air in an insulated, rigid, compressed air tank whose volume is a half cubic meter is initially 4 megapascals and 20 degrees Celsius. Enough air is now released from the tank to reduce the pressure to 2,000 kilopascals or 2 megapascals. Following this release, what is the temperature of the remaining air in the tank? Now, from your intuition and what you learned with the temperature in the temperature of the air in the tank, I have to say air in the tank at the same time. Tank. Air in the tank, would it be at 20 degrees Celsius, more or less? Less. Why? You got to somehow provide the flow energy of the exiting air at 20 degrees. So yeah, the temperature is going to be less.
The experience also.
The experience says so as well. That's right. All right, so let's draw the system and see what we've got. Here's the tank. Here's the valve. Air escapes. P1, 4,000 kPa. T1, 20 degrees Celsius, also known as 293 Kelvin. Okay. And the volume in both states, so I'm not going to put a subscript on it, is a half cubic meter. We know that the pressure in state 2 after the release of air is 2,000 kilopascals. Obviously the volume is the same. Okay, so anyone that's worked on this, how did you start it? What did you do? No one started it?
It is
Could you just find the mass and then,
from the mass, state one.
Mass at state 1, that's probably a good place to start. What did you find?
P1, V1, R, T1 is, what the number I came up with?
Yeah, if you got it.
23.78 kilograms.
23.78 kilograms, okay. Now, we've got a slight problem here because the mass in state 2 depends on the temperature in state 2, right? But we could write out the equation. We could say that the mass in state 2 is equal to P2 V, now I really don't need a 1, right, because the volume is the same, over R over T2. So this gives us a relationship between the mass in state 2 and the temperature in state 2. Notice that the pressure, volume, gas constant, those things are just numbers. Okay. What else could we do? We write a mass balance. Right? So the amount of mass that, let's say, either goes out or exits the system, let's put it over here. And of course, M1 goes with state 1. So the amount of mass that exits is simply the mass in state 1 less the mass in state 2. Notice I did that. I wrote that mass balance by inspection. I didn't write it as deposits, withdrawals, change in system balance, because if I'd done that, it would have come out this way. I'm not really worried about it. I just know that there's more mass in state 1 than there is in state 2, and the difference is just however much mass comes out. So here's a relationship that relates something we know to two things that we don't know. So essentially all we've done is we've kept our ignorance at the same level. Okay.
E is the mass exiting.
Mass exiting, that's right. E is supposed to be a subscript. I get tired of talking about MO. It looks like initial mass. M naught. Okay. It's mass exiting. Okay. What other equations do we have? One more.
Energy balance.
Energy balance. So help me write down an energy balance for this system. Now, did they tell us anything about heat transfer?
they said it's insulated.
It's insulated, that's right. So there's no heat transfer. So you can write Q equals 0. In other words, this is an adiabatic process. Did they tell us anything about boundary work or any propellers or anything in the system? No, in fact, there couldn't be any boundary work because there can't be any change in volume. If we take our system to be a system with mass flowing out. Now, if we take the system to be all of the mass, regardless of where it is, then there could be boundary work because the air leaves, but we keep a boundary around it, and keep track of it as it moves, right? Well, let's choose the system where we allow mass to leave. I think that's the better system anyway, because at state 2, the pressure in the tank is different than the pressure in other parts of the system if we try to keep track of all that mass, right? Temperature's gonna be different too, so we'll just let the mass leave the system. So help me write down the energy balance. Do we have any deposits? Nope. Looks like my bank account, right? We only have withdrawals. It only works for so long, we find out. Okay. So what withdrawal do we have? How do we quantify this withdrawal of energy?
Mass.
What mass? We've got 3 of them.
Out.
Exit or out, okay. Times? Enthalpy. Not U, H. Why H? Because it's flowing. So it's flow energy as well as thermal energy. Okay, does this need to be a deposit or a withdrawal? So is it negative or positive? Negative. That's it, right? That's all the transfers. That's equal to what?
M2, U2.
Essentially the change in the system, right? So M2, U2. In other words, the final energy in the system. Okay, less what? Less the initial. So what would that look like? Okay. Now, will the internal energy in state 2 and state 1 be the same? No. Why? Because the temperature is different. Right? We can't assume that the temperature is the same. That wouldn't make any sense. Will the mass in state 2 and state 1 be different? Of course, some mass leaves. All right? So how many unknowns do we have? Well, we don't know the mass that exits. We don't know the mass in state 2. We do know the mass in state 1. As far as energy goes, we don't know how much internal energy there is in state 2 because we don't know the temperature in state 2. We could get at this. I'm not saying we can go look it up. Maybe we could, maybe we couldn't. We know the initial temperature. So essentially, we know the initial thermal energy, right? How about the enthalpy of the exiting stream? We've got a small problem here. Because as mass comes out, the temperature of the exiting mass is going to do what? It's going to go down. We're going to keep looking at mass coming out, and we're going to see colder and colder and colder mass coming out because the tank is cooling down. Right? Now, how are we going to deal with that? Well, we have to. What's that?
Do it as the average over
This is the average, that's right. You were listening when I was talking. Good job. Most people at that point are like, I don't know what he's talking about, we'll figure it out later. Okay? But what I was saying is, when we have an unsteady problem where we need a property that's changing, we're going to have to evaluate it as an average. So we'll have to take the enthalpy exiting to be some average value. So what could we do? Well, we could say we'd like the enthalpy initially plus the enthalpy finally divided by 2. Just take the average of those two. Now, when I say 1 and 2, I'm not saying that the system holds enthalpy. I am saying that the mass that's flowing out when we're at state 1 is going to have more enthalpy in it than the mass that's flowing out once we reach state 2. Does that make sense? So all we're going to do is take some average value where these two depend on T1, T2, just like this depends on T1, and this will somehow depend on T2. Does that make sense? Questions,
I
comments?
was thinking you could just do CT delta T, but you can't.
Yeah, you can't because this is not a delta, is it?
Yeah.
It's not a difference. It's a sum. Now, we can do something like that. If we use our trick of the reference state based on temperature, then we could do CP T1 plus CP T2, right? Divided by 2. Because we've pulled that trick several times so far, right? A heat capacity multiplied by temperature, where the reference state is 0 Kelvin. Does that make sense? It's not a delta T, it's a sum there. And we could work on this one by saying this is going to be a CV T2. We've got to come up with something here as well, so we'll use CV T1 since T1 is known, and that's not so bad. Notice the unknowns kind of changed then, right? We have mass that exits as an unknown. We have the mass in state 2 as an unknown, but the only other unknown is the temperature in state 2. Now we have 3 equations, 3 unknowns, because we've got a relationship between M2 and T2, this relationship is the ideal gas law, right? Looks like a G. Ideal gas law. That's what relates T2 and M2. What relates the mass that exits at M2 is a mass balance. Okay? And the third relationship in order to solve all this is the energy balance. So I suppose, I don't know which of these two you'd say are related. Basically, it's all three are related together by the energy balance. But it's still just one equation that relates to the three. So this is a set of equations that we could solve.
First thing we can do, we can substitute M2 in to get rid of T2.
We could, what did they ask us for? Temperature, so I wouldn't want to get rid of T2, I'd want to get rid of M2. That makes sense? So what I would do is, so then, let's see, let me erase some of this. Let's pull this down and work on it. The mass that exits, I'm really not interested in. So let me write it as M1 less M2. Now I have to preserve the negative sign because it comes from here. This will be M1 less M2, but I don't want to write M2, I want to write this. P2V over R over T2. You see how this is the mass that exits? Okay? So that takes care of that. I need the enthalpy of the exiting stream, but I'm not going to write it that way. I'm going to write it as CPT1 plus CPT2 divided by 2. See that? Because you will have to FOIL here. Now fortunately, the temperatures are going to cancel, so you won't end up with a second order term from this side of the equation at least. Now this will be equal to M2U2. I don't want M2. So I will write P2V over R over T2 for the mass. For U2, I will write CV T2. Okay, so that takes care of these terms. I have to subtract off the mass in state 1, but the mass in state 1 is unknown, so I can simply leave it in. CV T1. And this is the equation then that we will solve for T2 because it's the only unknown. Now if you don't feel like solving for this algebraically, I don't blame you. But notice the T2 here will cancel, and this is really not so bad. The right-hand side is just a number. Okay? You can plug in numbers that were given or that we've calculated and take care of that term. Over here, when you multiply these two terms, the temperature is going to cancel. When you multiply these two terms, there's no T2 in that. So you're going to have a constant. Then you're going to end up with the product of these two terms and the product of these two terms. And so you'll have one term that has 1 over T2 and one term that has T over. Okay? So then you'll have to multiply by T2 and you will end up with a squared term. So this is a quadratic equation. It might be easier just to plug this into Excel and do a gold seek to solve for the temperature in state 2. Okay? I see deer in the headlights, folks. You guys okay?
It's been a couple of years since I've had to run out and set simultaneous equations. That's all.
Okay.
All right. They're not too bad.
All I did was sub in everything to get rid of
I
stuff.
thought this was gonna be a really simple problem when it came to the arithmetic. Because it was short.
When the numbers go up.
Yeah.
Sure.
It was like there was less words in this problem.
This is a correlation of words to difficulty.
The relationship is broken.
I think this is a little bit more than just broken.
It's like the 214 class or whatever, the 2.4 now, or whatever, the electronics class. All it is algebra, but I think it's what it gets to. I mean,
I think it's been since statics, actually. I think statics was the last time that I had to do an
We
equation.
should have done it at 220. How did I miss that?
It might
In
have
the
been
frame?
dynamics.
John?
Yeah,
Oh, no.
I don't know who's missing, but let's help them out a little bit. They'll probably want to see this.
it's pretty good.
There's a little bit more of the board. Hopefully the resolution's high enough where it can be zoomed in on. Okay. You tired of chapter 5 problems?
Yes.
No.
Is that the last one or no?
Not so tired that I want
That's the
something
last
chapter
one.
6.
I'm sorry?
Not so tired that I want something chapter 6.
Let me give you a quick introduction to chapter 6. Keep it light and airy and I'll let you go over it, okay?
how early?
Whenever we get through the library
Yeah,
stuff, and it starts to look hard, how's that?
Like to quantify all that.
That's the quiz tonight.
No, we don't have a quick.
Chapter
Oh, you
6
mean
is a
the quiz.
chapter in a book about heat.
What?
Online quiz.
All right, so far, what have we done? Well, what we've done is we've played around with mass and energy balance. That's really what we've done. Okay? Now, some are more difficult than others, some problems are harder than others. But the idea is that you gotta keep track of mass, you gotta keep track of energy. That's why they're called balances. Because this is nothing more than accounting with some physical principles in it. So, it turns out that there's another piece to this, though. It's not just a balance of energy. It turns out that energy has a quality, because think about it. Remember Joule's experiment we talked about a little earlier? 2 flasks, one had high pressure in it, the other had low pressure in it. You guys know as well as I do from experience that high pressure air was more valuable than the low pressure air. How do you know that? Well, one way you know it is by the fact that getting back to that situation would require an air compressor, right? You have to run that air compressor to suck up air from the, re-evacuate the one side and push it over into the side that originally contained all the air. You gotta pay for the energy to do that. So, energy balance told us that there was no energy lost, but there was still a loss of something, right? And it was the quality or the usefulness of the energy. It turns out there's a whole lot of energy in the universe. Okay? The universe may be above a temperature of absolute zero. If you take the average energy in the universe, it's above absolute zero as far as I know. Or look at the moon, where's what we call it. Point is, there's a lot of thermal energy out there by virtue of the fact that there's a lot of mass out there besides what's here on Earth and besides what's on the sun. But is that energy actually all that useful? Can we harness it for anything? We could get it closer to us? No. There's no quality in that energy. So what we're going to do is we're going to find out how to deal with the quality of energy. Okay, because it turns out that when Joule released that high pressure air and allowed it to flow into the other side, he created something. He created some entropy. Okay? He created some randomness. And so what we're going to do is if entropy helps us measure the quality of energy, then we'd like to know about it. We'd like to use it in order to make sure that the energy we're trying to take advantage of is actually useful and actually worthwhile. Turns out that the energy sources we use have very low entropy. Okay? So that's one of the reasons we use it. Anyway, so we're going to answer the questions. Where are we going with this? Well, we're going to couch this discussion in the answer to 2 questions. What's the most efficient heat engine, refrigerator, or heat pump that we could theoretically make? Because, everybody's interested. If you go on YouTube and you look up 100 mile per gallon carburetor, you'll find all kinds of stuff, right? You'll find people that have claimed they've done it. You'll find people that have claimed that Shell and BP got together and destroyed it. You'll find all kinds of interesting stuff, right? You can spend the rest of your life looking at this stuff. But what's the best we could do? What am I talking about with the heat engine? Well, in just a few minutes, you're looking forward to going out and jumping into your heat engine, turning over the ignition and going home, right? The engine under the hood of your car is a heat engine. And so, anyway, what's the best we could ever do? We've gone from the 70s, where we had, maybe 15, 16, 17 miles per gallon tops. Now the 2000s, where we're supposed to have flying cars. At least that's what Back to the Future taught us, right? Where are they? And a jetpack and a hoverboard too. Remember the hoverboard? That's not happening.
He is bringing his shoes in.
Okay. So what's the best we can ever do, right? And by the way, what does the efficiency of all these devices depend on? Well, we'll go ahead and give you the answers. Here they are. A completely reversible heat engine, refrigerator, or heat pump would be the most efficient. So that gives you a new question, right? What the heck is reversible? What does that mean? Well, let me give you a quick preview of that. Was Joule's experiment reversible? No, it wasn't. And that's how you know that entropy was created and the quality of energy was depleted. Not the quantity. There's still just as much energy, but the usefulness of that energy was reduced. Okay? All right, the efficiency of those devices, the answer, what does it depend on? Depends on the temperature, the heat source, and the heat sink. It's a heat source and a heat sink. Well, let's find out. So let's see, it turns out there's a second law, not just the first law that says energy is conserved, but there's a second law that will tell us whether or not these processes actually go forward. So let's start off by looking at the first law, which is just energy conservation, and see which of these cases would break the first law. Remember, the first law is that energy is conserved. Okay? We have a paddle wheel where we put work into water that would increase the temperature of the water, and so heat transfers out. Does the first law say that this is impossible? No. As long as the work that goes in comes out as heat, or we leave behind a certain amount of energy here and some heat comes out, no problems, right? What does the first law say about heat coming into the water to increase the temperature of the water such that the water turns the paddle wheel and work comes out? Does the first law, energy conservation, say that that can or cannot be done? Why not? As long as the heat that comes in is equal to the work that flows out, the first law says fine, and your experience says, heck no, there's something else going on here, right? Well, we'll get to that in a minute. The first law is not violated in either one of these cases. Well, this gives us an idea. Why don't we use heat? In fact, you could probably make a YouTube video on this showing exactly how to do this and get millions of hits and make a little bit of money, okay? All right, so let's put heat into this fluid that surrounds the paddle wheel such that that paddle wheel will turn and it will raise a weight.
We just put an electric motor right there. Shaft.
Yeah, in fact, I did something kind of interesting when I taught this class before. I had the students build perpetual motion machines of the first and second kind, which I'll review with you later, and come in and sell them to me. One student was very clever. He decided that he was going to make a system. He had, in fact, if I've got it, I'll show you the video, but he had a central tube with some PVC fittings coming off it. So basically he had arms in a wheel shape coming off this, with caps on the thing. He put a little bit of water in it. He brought it in to demonstrate. He put a rope around it to tie it and keep it from turning on its own. Okay. The idea behind this was that the essentially the water in the wheel. Imagine with just two tubes that are capped off, which can allow flow here. Basically, as the wheel comes around here, the water is going to fall to this end, causing a large moment arm, all right, which will rotate it around. But when it comes up here, the water is naturally going to flow more to the lower area. So this should just keep going, right? Now he was very clever. He did not try to demonstrate it for us in class. Instead, he shot a video at home of him doing it, so that us as investors would invest in his idea. And he said, now you got to hold it still because it'll take off on you, right? So he steps away from it, and it started turning. It started turning faster and faster. He grabbed a hold of it and said, you know, I'm scared to let it go too far. You know, but I can't demonstrate it for you right now. I don't have any water available. So, but just in case I've got to tie it off. So how many people are interested in investing in this? Of course, none of us were, because we knew it was a perpetual motion machine of the first kind where it was creating energy from nothing. Okay? Now, how do you suppose on the video he made the wheel turn? He didn't have a hidden weight. He confessed to us that he had a fan outside, and the fan turned the system. So he just had a fan blowing continuously, and that would make the wheel accelerate. Okay. So anyway, so you might be able to sell something like this. I don't know. He tried. We didn't buy it on it, but maybe he's found someone who needs that. How about a cup of hot coffee sitting off to the side that loses heat? Sure. There's internal energy there, and heat could be transferred away from hot coffee. So the first law says these are fine. How about the second law? Well, basically, the first law says no, the first law is not violated. I'm happy with all this. All this could happen.
The second case.
The second case, the second law says, well, yeah, this is not a problem. In other words, do we really observe these things? No, we do not observe that one, right? The second law says this is not ever going to happen. How do we know? Honestly, we don't really know, but we do know that in a bulk sense this never happens. I've been reading some papers that say that actually on the macro scale this does happen, but the integrated effect, the average effect, is that this does not happen on the macroscopic scale. That's interesting. But anyway, it makes sense if you stop to think about it that internal energy is just motion on the molecular scale. Right? So the idea that you could somehow get that motion to combine and give you a larger motion is not unreasonable.
Where would you have to find out to make all the energy move in the same direction in order for that?
Is that what the liquid metal is? Have you seen anything about that?
I haven't seen the liquid metal
I should
special.
look that up. There's a
Is it
They
just
have-
mercury? That's what we're
No, they have a liquid metal that's being developed in China that moves on its own.
That's interesting. I don't know.
It's
What's
very
the source of
interesting to
that?
watch it.
What's the source? Well, it turns out you
The
can
source
put,
of energy, I think it's heat, it would have to be heat, but
okay, well, maybe a heat engine then.
I
don't
think-
know.
that's what it is.
I
Okay.
think you saw that, but they're making water move on its own by heating up a surface real hot, like a sauce, or
So you use a surface tension, because you can get.
surface station, but they're making it float in the air, and they make stair steps so that it pushes itself forward each time, because
So
of the
you just
angle.
type in Chinese liquid metal.
I will, I'll look at it. I know you can
I think
also
we're talking about the
use,
same thing.
there's also chemicals you can use, you can put, I forgot, I was learning about it in fluids, because he's assigned videos, and so I watched a bunch of videos in that class, but there's some chemical that you put in with mercury, and the mercury will actually chase this chemical, basically, it's a chemical reaction, and the chemicals dissolve. But anyway, so the second law also says you cannot do this is not absurd. But, of course, this case is absurd. We know that heat only flows from hot to cold. So basically, for a process to occur, the first law has to be satisfied, but also the second law has to be satisfied. Okay, so let's define thermal energy reservoirs and we'll call it quits. So here's Calvin and Hobbes watching TV, and you know that there's energy going into the TV because the TV's plugged in, right? Now, if you ever put your hands over the old TVs, or even the new ones, you can feel heat coming off of them, right? Now, does the air in the room, since there's heat coming off the TV, does the air in the room change temperature? Technically, yes, but it's so small you never notice it, right?
Depends on what size of room you're in. My room, I could definitely tell I have my PS4 and my TV on, it definitely gets warm.
Okay, sure. So it depends on the size of the room, right? Well, the idea of the thermal energy reservoir is that it's something large enough such that when you put thermal energy into it, or you take thermal energy out of it, its changing temperature is essentially zero. That's a thermal energy reservoir. Why would we talk about them? Well, we'll need them to take out some of the complexity of real systems, okay, so we can analyze what's going on with those systems. So we'll have thermal energy sources of basically where we'll transfer heat from them, and thermal energy sinks where we can throw thermal energy away and not change the temperature. So the temperature change of any source or sink is zero, regardless of how much thermal energy you put in or take out. So this concept of a thermal energy reservoir is going to be very important. All right.